Welcome to the third installment of the calc Semester 1 review. This number 17 is another interesting problem. It's one of those where we don't know the coefficients on the quadratic function that we're given, but we do know some information about it. So 1, 3 is a point. It's a solution to this equation, and the tangent at A has a gradient, which means slope of 8. So that, again, the slope implies that I'm going to have to take the derivative. But first things first, let's take that point 1, 3. F of 1 has to equal 3, so that means if I put 1 in for x here and here, that I get 3, which means p plus q equals 3. I don't know what to do with that yet, but I'm going to take my other bit of given information. Tangent to the curve has a slope of 8 when at point A. So I take the derivative. Notice the derivative of px squared is 2px, just treat p like any other number, and the derivative of qx is just q, just like the derivative of 5x would be 5. Now I substitute 1 for x, and I get 2p plus q equals 8. So if p plus q equals 3 and 2p plus q equals 8, then we can have what's called a linear system. We can solve this using substitution or elimination. What I chose to do was to subtract the red equation from the purple one, because then the q's would subtract out. 2p minus 1p is p, 8 minus 3 is 5. So if p equals 5, go back up in here, 5 minus 2 equals 3, so q has to equal negative 2. That's what I needed to do, was find p and q. Now to verify, first of all I put p and q into the equation, put the equation that I found into Desmos, and then verify that 1, 3 is in fact a, that 1, 3 is, sorry I lost my track, I had a notification on my iPad. So I was trying to say, 1, 3 is a point on the line, point A, where the slope is 8. So I found the line that goes through 1, 3 using the point slope form and a slope of 8, and that's indeed tangent to the curve where it should be. So I think this is the last problem from this review set. There are other problems on the packet that I gave you. If you're running out of time, emphasize the calculus ones. You probably don't have to do the quadratic ones as much. So just focus on that. And then the work that I did on this packet deals with some of the most challenging problems that you'll have to face. Not to say that they'll exist that challenging on the assessment, but if you can handle the work from the problems in these videos, then you should be fine on the assessment, because it'll be probably a little easier. Alright, so finally we have another quadratic function, and it says that there's going to be a normal to the curve at the y-intercept. So it just wants to show you what we have to find that the equation is this. So it's already gave us the equation. We just have to prove that that's going to be the equation of the normal. So to do so, once again, we need to take the derivative. We have the original function, take its derivative using the power rule. Or sorry, first thing is I recognize that the y-intercept is 0, 2.5. Then I take the derivative, set the derivative equal, or sorry, I'm going a little ahead of myself here, let me stop. First thing I evaluate is where is the y-intercept of the function f of x. F of 0 equals 2.5. Done. Second thing is I take the derivative. This way I can find the slope of the tangent line when x equals 0. That's where here I found f prime of 0, which was 2. I don't need the equation of the tangent line. It says n is the normal. Recall that the normal is perpendicular to the tangent line, and slopes of perpendicular lines are always going to be opposites. One goes up, the other goes down. And they're always going to be reciprocals. One is steep, one is flat. So the perpendicular line is going to have a slope of negative 1/2. This is good because it shows that y equals negative 1/2 x is the equation of the normal that I'm looking for. We just have the 2.5 as the y-intercept, which is here. That's a y-intercept. So clearly the equation of the line I'm looking for is most definitely what they said it would be. To verify, oh, sorry. We'll get to the second part of this problem, and then we'll verify everything. It says it's asking for the coordinates of the other point of intersection from the normal and the curve. Just real quickly, what we have here is a parabola, and the parabola is going to have a shape that's going to look something like this. And we have a normal, which is going to be perpendicular to the curve at the y-intercept. It's saying that there's this other point of intersection over here somewhere else. Where is it going to be? It's going to be at the place where the line will intersect the parabola again. So we have f of x, the given function, and we have the line of the equation of the normal. All we have to do is set the equation of the normal equal to the function and find out the x values that make them the same points. We already know one is going to be when x equals 0, but we'll do the algebra to see where the other one is. First, we're going to subtract 2.5 from both sides, and then I'm going to double both sides of the equation and actually multiply both sides by -2. So -2 here gives us a +1. 2 times -2 is -4. -1/2 times -2 is x. So you can see I have a much easier equation to deal with. Subtract x from both sides and we get x squared minus 5x equals 0. Factor out an x, and then we could use the zero product principle. X is either 0 or 5. Now we already know that x equals 0 was going to be one of the solutions, so that's not a surprise, but the other x equals 5 is the other point in this. Well, I lost sight of my picture. Here it is, in that little graph. Anyway, all I have to do is evaluate f of 5 then, put in 5 for x, and we get the following value. X equals negative, or rather 0. So 5, 0 is the place where the normal is going to intersect the graphic. And now my picture was a really bad sketch. It's up here somewhere. So I'm going to go to Desmos, and sure enough, when I put this into the graphing calculator and I put in the equation of the normal and the given function, the other intersection is 5, 0, just like my work said it would. So thanks for watching. I hope this was informative. Remember, in all of these videos, I was talking very quickly, trying to get through the videos in a short amount of time. Please don't forget to pause the videos, make sure you understand the work, and the notes have already been provided in haiku, so enjoy. Merry Christmas.